So I've got a great pleasure to talk about a series of joint works with collaborators, Aurélien Alfonsi, Raphaël Coyot, Damiano Lombardi and Luca Nena, about some sparsity results, about some approximations based on moment constraints. I'm going to explain what I mean by this later in the talk, of some functionals which appears in density functional theory and which are related to optimal transport. So specifically in this talk, I'm going to make a specific focus on the Lieb functional, okay? But I'm going to draw to this rather in the end of the talk, okay? So here in this talk, I will first talk about the link between density functional theory and optimal transport as a starter, and then about this moment constraint approximations that we've worked on. Okay? Ah, si, c'est bon. Okay. So let me start with the link between density functional theory and optimal transport. So first, a brief recap. So here in this talk, we are going to consider fermions and not bosons, okay? And our holy grail is a many-body Schrödinger model for this type of system. So here in the talk, I'm going to consider the physical systems composed of n electrons, okay? The state of which will be described by a wave function. That's a function defined over R3 n with complex values, okay? And, sorry, poof. And I'm going to assume that this system of electrons will be subject to some external potentials that will be denoted by V, which is a function defined over R3 with values in R, including plus or minus infinity. You can think about the Coulomb interaction potentials generated by nuclei within a molecule, okay? And then the wave function psi of my set of n electrons will have to belong to an admissible set of wave functions, which I will denote by an the rest of the talk. That corresponds to the set of wave functions which corresponds to the state of electrons with finite kinetic energy. Okay, so this is simply the set of wave functions that are L2, the gradient of which is also L2, and that are antisymmetric with respect to permutation of the order of the electrons, and with L2 norm equal to 1. Okay, so here, for a given external interaction potential V, I'm going to denote by Eg of V the ground state energy of my system of electrons. Okay, so Eg of V is simply given as the solution of a minimization problem. Okay, what you're looking after, you're looking at the minimal value of the energy of the system of electrons over all possible admissible wave functions psi. Okay, and the energy of the system of electrons is composed of three terms. So the first term is the kinetic energy of the electrons, that is the squared norm of the gradient of psi up to some 1/2 factor here, okay? Then you've got the electron-electron interaction energy, that is simply the integral of the Coulombic interaction times the square modulus of the wave function psi. And here this is the Coulomb potential is given by this expression here, okay? So you're looking at all the Coulombic interactions between all the pairs of electrons. And you've got the last term, which is due to the effect of the external potential, okay, which writes under this form here. All right, and so we are looking at this minimal value of the energy among all possible admissible wave functions for our system of n electrons. Okay, this is Eg of V. So very simply, then the ground state wave function and the ground state energy solution to a linear eigenvalue problem, okay, associated to the Hamiltonian of the electrons, which is this operator here, and you've got the three terms related to the three terms in the energy, of course, which is here the minus Laplace operator related to kinetic energy. The C here is the Coulomb potentials of the electrons with one another, and you've got here the last term related to the related to the external potential V. Later in the talk, I'm going to use a notation H and V to highlight the dependence in the external potential. Okay, and H and 0 will be a notation to refer just for the two first terms in the operator, containing the Laplace operator and the electron-electron Coulomb potential. Okay. Then the problem with the previous eigenvalue problem, is that the wave function psi is defined over a very high dimensional space, okay, R3n. And so in practice, solving these linear eigenvalue problems with standard numerical methods is just out of reach because of the curse of dimensionality. And that's the reason why theoretical and computational chemists have worked on the development of the so-called density functional theory, which provides a theoretical framework that is amenable to practical numerical simulations in the end. So let me explain to you what this is about for those of you who are not familiar with density functional theory. Here, just let me introduce some notations that will be used later in the talk. For any admissible wave functions psi, for my system of n electrons, then the electronic density associated to psi will be a function rho psi that will be defined over R3, okay? That is just up to a normalization factor equal to the integral of the squared modulus of the wave function of psi over all vectors of R3 except one. Okay, so this guy actually gives a probability density of finding one electrons out of the n somewhere in the space. Okay, and you see here, density functional theory. The main idea of this theory is to consider electronic densities instead of wave functions. Why? Because these electronic densities are defined only over R3, and so these are objects that are much easier to compute from a practical point of view than wave functions. Okay. And then the so-called, you've got a very nice result that enables to fully characterize the set of electronic densities that you can get out of admissible wave functions. More precisely, so this set will be noted by IN in the rest of the talk. You can prove rigorously, and this was proved in this series of papers, in particular by Levy and Lieb in these papers, that the set of electronic densities that you can construct out of admissible wave functions is simply the set of electronic densities that are non-negative, the integral of which is equal to n, the number of electrons, and the gradient of the square root of which is square integrable. Okay, and so this is a very nice characterization of the set of electronic densities that is fully explicit, and which does not require anymore to make the use of wave functions anymore, which is very nice. And then you've got the Hohenberg-Kohn theorem. That is the starting point of all this density functional theory I'm talking about, which is a very wonderful result. And it states the following thing. It states that for a given external potential V, the ground state energy of your system of electrons, you can write it equivalently as the solution of a minimization problem where you minimize some functional which only depends on the electronic density of the set of electrons rho. Okay, so more precisely, you can rewrite it as the minimal value of some quantity which depends on rho, a given electronic density in this set IN, plus some terms that can be written explicitly in terms of the external potential V, that is just integral of V times rho. Okay? And this Hohenberg-Kohn functional FHK of rho is given as by the following expression, okay? For a given electronic density rho in this set IN, it's equal to the minimal value of the sum of the kinetic energy of a wave function psi plus the electron-electron interaction energy of the same wave function psi over the set of admissible wave function, the electronic density of which is equal to rho. Okay? So here, two comments. So first, as I told you, actually this minimization problems too here looks much nicer from a practical point of view, because you only need to minimize over electronic densities instead minimizing problems over wave functions, and electronic densities are only defined over R3 and not R3n. So this is nice. But of course, there is no free lunch. This Hohenberg-Kohn functional, actually, its expression, well, requires the resolution of a problem that is almost as difficult as the original many-body showing a problem, since you see to obtain this Hohenberg-Kohn functional for a given electronic density rho, you still have to solve a minimization problem, the unknown of which is a wave function. So it seems like you haven't gained anything, but still, so this Hohenberg-Kohn functional in practice, nobody knows how to compute it exactly. Okay, this is a problem that is as difficult as the original many-body Schrödinger problem from the start, but nevertheless, theoretical chemists have worked on deriving approximations of it, that then in turn are used in such a kind of minimization problems. Okay. And that's all about density functional theory and models that are used in computational chemistry out of this theory. Well, the goal is to try to find approximations of this guy that can be used for practical computations in this type of density-based minimization problems. Okay. So here, that's exactly what I've just said. I'm not going to the zoology of approximate models that have been derived out of this density functional theory, because there is a, as I use the word zoology, there is a real reason. It's a whole zoo, okay? We can talk about it for days and days and days, okay? And that's not the aim of my talk here. I just want here to point out, I'm going to talk about some particular examples of these approximations that are related to the Lieb functional, and I'm going to talk about in the sequel. Okay. Here, the important point I want to emphasize is that this Hohenberg confunctional is not convex. Okay. So even if you knew it exactly, solving this type of minimization problems could be not a trivial task from a practical point of view. Okay. And this is one of the motivations that was under the work of Lieb in this paper in 1983. For this reason, he introduced the convexification of this Hohenberg confunctional. And that's precisely what's called the Lieb functional. Okay? So the Lieb functional for a given electronic density rho in the set In, it will be denoted in the talk by FL of rho. Okay? And as it is defined as a convexification of the Hohenberg confunctional, it writes as a solution of this minimization problem, where you look at all possible convex combinations of densities rho I with convex weights alpha I, okay? So that the sum of for I belonging to n star of alpha I rho I is equal to rho, okay? Of this quantity here, okay? That is a convex combination of the value of the Hohenberg functional taken at the density rho I. Okay? Actually, out of the convex theory, you can still have the following results, that the ground state energy of the system of electrons under some given external potential V is still the solution of a similar minimization problems defined in terms of electronic densities, but where you have replaced the Hohenberg confunctionals by this Lieb functional, by its convexification. Okay. And so, even if the computation of the Lieb functional looks even more complicated than the Hohenberg confunctional, at least there is one thing that we've gained here, which is that this minimization problem is actually the minimization of a convex functional in terms of rho. So just keep that in mind. It will be important for the sequel. Okay. Actually, this Lieb functional, you can give it another interpretation, which is exactly equivalent to the one I've just written. You can write it as a solution of the minimization problems out of mixed states instead of pure states. Okay. More precisely, so this is typically a slide that I show to people that are familiar to optimal transport theory, but not really mathematical physics. So I guess this will not be a problem for people in the room, okay? But just to make things clear, more precise, okay? Here, I will denote by calligraphic H0 node the space of wave functions that are just L2 and antisymmetric. So here, I don't put into H0n psi may not have a squared integrable gradient, okay? And I will denote in the sequel by S1 plus the set of self-adjoint non-negative operators that are trace class and that act on the space calligraphic H0n. Okay? So keep in mind this notation. So since for any operators belonging to sigma 1 plus, since they are trace class, you can diagonalize them, okay? And so there always exists a sequence of non-negative eigenvalues alpha I, the sum of which is finite, okay? And orthonormal basis of associated eigenvectors, okay? So that for all I, gamma psi I is equal to alpha I psi I. And then to any such operators gamma, trace class operators, you can define an associated electronic density, which will be denoted by a rho gamma of x, and which is defined as a sum from I equal 1 to plus infinity of alpha I rho psi I of x. Okay. Here again, alpha I are the eigenvalues of gamma, and psi I are the associated, some associated eigenfunctions. Okay, with this notation in mind, actually, the Lieb functional, you can write it equivalently as the following minimization problems. FL of rho is equal to the minimal value of the trace of the Hamiltonian without the external potential, okay, Hn0 times gamma, okay, over all gamma in the set sigma 1 plus, so trace class non-negative self-adjoint operators, the electronic density of which is equal to rho, okay. And actually, if you look at this problem under this form, you can recognize that the value of this Lieb functional actually reads like some particular instance of quantum optimal transport. And this has links with some works by Goltz, Moore, Paul, and there is also Laurent Laflèche in the room who has worked on a similar type of quantum optimal transport problems. So just for the experts in the room of this type of problems, this looks like a quantum extension of a Kantorovich formulation of optimal transport problems. Okay, so just a parenthesis. All right, and having this point of view will be very useful in what I'm going to tell you in the rest in the sequel. Okay, so just to remember, Hn0 is just the Hamiltonian without the terms linked to the external potential. Okay, and so you can rewrite this trace explicitly in terms of the eigenvalues and the eigenfunctions of the operator gamma. All right? So that's the first functional related to density functional theory and optimal transport I wanted to tell you about. So as I told you, it reads like a quantum optimal transport problem. Okay. Now I want to tell you about the second functional that will rather read as a classical optimal transport problem, but it's useful for me to introduce you these two functionals because there will be analogies in both cases and some things are easier to understand for the classical optimal transport problems than for the quantum optimal transport problem. Okay. So keep this guy in mind, okay, and let me introduce you the second functional I'll be interested about that will read as a classical optimal transport problem. This guy is actually what's called the strictly correlated electron limit of the Hohenberg-Kohn functional, okay? And this is a quantity that was first considered in a series of work by Seidel, Gori, Giorgi, and Savin, okay, in the 2000 years, okay? And it reads as follows. Introduce some parameter h, positive parameter h that has a vocation to become small at some point, okay? And define an h-dependent Hohenberg-Kohn functional, okay, that is the solution of the minimization problem very similar to the original Hohenberg-Kohn functional, but where you put this parameter small h in front of the kinetic energy term, okay? Then, you can consider the limit as this parameter small h go to 0 of this h-dependent Hohenberg-Kohn functional for a given electronic density rho. And this is exactly the definition of this strictly correlated electron limit. Okay. And so that's a guy that reads actually as the solution of a particular classical optimal transport problem that I'm just going to write right now. And this is the guy. Okay. So just to give you an intuition of where optimal transport stems from in this picture, okay, you can make the following remark, which is that if you consider a wave function psi in this admissible set of wave function an, well, very naturally, the squared modulus of psi is the symmetric probability measure over R3n, okay, and in particular, the terms related to the electron-electron interactions in the system, it simply reads as the integral of the Coulombic interaction potential C that is seen as a cost function in terms of optimal transport theory against this probability measure gamma psi. Okay? And so, if you consider gamma any symmetric probability measure on R3n, what plays the role of the electronic density associated to such a measure? Well, actually, it's a marginal of this probability measure. Okay. And so, actually, it has been proved rigorously in this series of work that this strictly correlated electron functional for a given electronic density rho reads as the following minimization problem, where you consider the minimal value of the integral of the cost against any symmetric probability measures, gamma defined over R3n, with marginals equal to the electronic density rho. And that's where this guy is what's called the multi-marginal optimal transport problem, written in the counter-average formulation form. So I don't know how many people are familiar with this in the room. So that's where optimal transport theory comes into play. So here, just a brief recap about these two functionals that I've introduced you. The first one was the Lieb functional, and reads as a minimization problems of a non-negative trace class self-adjoint operators. Okay, the electronic density of which is equal to rho. Okay, so this is some particular instance of quantum optimal transport problem. And the second functional is the strictly correlated electron functional. Okay, and this guy reads as minimization problems over the set of symmetric probability measures defined over R3n, the marginals of which are given as rho up to some normalization constant. Okay, so you've got these two pictures. Okay, first quantum optimal transport for the Lieb functional and classical optimal transport for this SCE functional. Okay, and so these two functionals, especially this one, have drawn some attention, in particular from people in the optimal transport theory communities that are doing computations. Okay, and there have been some recent efforts on the design of numerical schemes to solve these types of problems. Okay, the difficulty being, well, the dimension of the state space. And okay, because if you use some standard ways of discretizing this type of problem, you also have the curse of dimensionality coming into play. But still, having this optimal transport point of view helps in designing some particular schemes that enables to circumvent this curse of dimensionality. Okay. And so, just why does the curse of dimensionality comes into play? For instance, the classical optimal transport problem, a natural idea would be to discretize these probability measures as the discrete measures defined over a Cartesian grid of points, and of course, then the dimensions of the problem scales like exponentially with the number of electrons. Okay. But still, with this optimal transport point of view, you can think about alternative ways to compute approximations of this problem. Okay. So here I'm putting another exhaustive list of such contributions in this effort. Okay, in this direction. Okay. The most one of the first initiative was to rely on the so-called Thin-Korn algorithm, using some regularization with the Kullback-Leibler entropy functional. Okay. There are also some other types of initiative. Here I'm mentioning the genetic column generation algorithms that was developed by Frieseke and Vöckler and other collaborators. I'm going to say a word about this later. Okay. And they rely on sparsity results of the structure of minimizers of some discrete approximation of the classical optimal transport. Okay. And here, what I'm going to tell you about in the rest of the talk is about some other types of discretizing where we use moment constraints. Okay. And I'm going to give more details about this series of work in the rest of the talk. I just want also to mention that there is a recent contribution by Rodrigue Lelotte, where he introduced an external dual charge approach and together with efficient Monte Carlo sampling strategies in order also to solve all this is about the classical optimal transport problem. Okay, so the SCE functional. Okay. And so here I'm going to tell you some results we obtained first for the classical optimal transport problem, but because that's how we got into this field initially, and then about the Lieb functional, that is the quantum optimal transport problem. Okay. Are there questions so far? No. Yeah?
Maybe more of a comment or partly question on the terminology. So what you call the Hohenberg-Kohn functional, I think is what is usually called the Levi-Lieb functional.
Yeah,
it's certainly not the functional that Hohenberg and Kohn introduced.
No, you're right.
It's called the Hohenberg-Kohn theorem. It's not what people usually call the Hohenberg-Kohn theorem.
Well, that's
So the Hohenberg-Kohn theorem usually states that given a ground state density rho, if it comes from a potential V, that potential V is unique, and that uniqueness is used to construct the Honnenberg function.
Yeah, okay. So sorry if my terminology is not the exact one.
Theorems in this paper. So the first is what you said, and the second is exactly what she said.
No, but the domain is not the same.
Sorry. So sorry if the terminology is not the exact one. So the theorem are right. Okay. Sorry if I should have called it the Levi-Lieb, but sorry. I hope you're still with me for the rest of the talk, despite of this. Okay. Everything I said was true. Okay. I'm now going to the moment constraint optimal transport problem. Okay. So here, what is the philosophy? So as I told you, if you want to consider classical discretization for this type of, for now, let's stick to the classical optimal transport problem for the sake of simplicity. What you would do is that you would introduce a discretized Cartesian grid of the state space and approximate the probability measures as discrete probability measures charging points of this Cartesian grid. Okay? Here we don't want to do that. We don't want to discretize the state space. We want to keep the state space continuous for reasons that will be clearer in the rest of the talk. Instead, the way we introduce a discretization of these optimal transport problems is to relax the marginal constraints, so the constraints related to the electronic density in both cases, okay, which are infinite dimensional constraints, by a set of finite scalar valued constraints that are related to moments, okay? So more precisely, here, sorry, for the sake of simplicity, I'm going to assume that the density rho will have compact support. I can relax this assumption, but it makes things just technically more complicated, and this is not useful to understand the rest of the talk, okay? So, as I said, I'm going to introduce approximations that relies on moment functions and moment constraints instead of a full marginal constraints. So here I'm going to consider a sequence phi m of functions that will be continuous over R3. I'm going to assume that the first function of this sequence is just equal to 1, okay? And then that I have a natural density assumption on this set of this phi m function, in the sense that if I consider a continuous function defined over Q, the compact support, and if I look at the infimum value between Hennenfent of f minus the best approximation in the span of the first big M values of the sequence, while this quantity goes to 0 as big M goes to infinity. Okay? So this is a natural density assumption on this sequence of finite dimensional subspaces. Okay? That has a span of the first elements of this sequence. And then for any integer M, I will denote by rho M the moment of the electronic density rho associated to the moment function phi m, that is just integral over R3 of phi m times rho. Okay?
Is it important that it's not only powers? You want to take general?
I want to take general, well. I want to take general for reasons that will be clearer later on. But you can think about polynomials for now, but they will be later. Okay, and so, as I told you, now I'm going to consider relaxed approximations of the exact problems, classical and quantum, okay, where instead of imposing the full marginal constraints, either in the SC case or in the Lieb case, I'm going to replace this constraint by only the first big M moment constraints associated to the first big M elements of my sequence of moment functions, okay? This gives rise to approximate problems, okay, that depends on the set of moment functions, and big M, the number of moment constraints that I impose in the problem, okay. And of course, because here I'm considering minimization problems that are defined over minimization sets that are larger than the ones of the exact values of the SC functional and Lieb functionals, these guys are approximation from below of the exact quantities, okay? And this is a particular instance of generalized moment problems that were studied by Lasser in particular. Okay, and so we've got two approximations in the classical case and in the quantum case. Then, of course, there is very natural convergence result, which is under these assumptions, natural density assumptions on the set of moment functions. These approximate values do converge to the exact value as big M goes to infinity. Okay. There are links also with works by Louis Garrigue and Rodrigue Lelotte, in the sense that here we can get also this convergence result under different assumptions on what plays the role of these moment functions. Okay, so this is just a safety check, okay? What's interesting is that when you consider this relaxed formulation with a fixed number of moment constraints, you can prove that there exist minimizers that have a very sparse structure, okay? So let me first, this is proved both in the classical and in the quantum case using the so-called Chakalov theorem. Let me first state the sparsity result in the classical case, okay, because it's easier to understand. Remember, in the classical case, we are looking for minimizers that are probability measures defined over R3n. What this Chakalov theorem says, it says that we can find some minimizers of the moment constraint approximation that rise like the symmetrization of a discrete probability measure, which charges only a number of points which can be chosen to be at most equal to the number of moments plus one. Okay? So this guy, if you can have access to such a guy, you can have access to a minimizer of this moment constraint approximation of the SE functional. And what is very nice is that this such a guy has a very sparse representation in the sense that in order to identify it, you need to identify the weights here, WK, and the points xk that belong to R3n, but there are at most big M plus one of them. And so the complexity of this representation only scales like M, the number of moment constraints, times n, the number of electrons, which is to be compared with the complexity of classical discretization on Cartesian grids that scale exponentially with the number of electrons. So this sparsity is quite nicer in the sense that then you want to use it to design some numerical schemes when n is large. Okay? So that's the sparsity result that you get for the SCE functional, moment constraint SCE functional, which again is a classical optimal transport problem. Using again the Chakalov theorem, you can get a similar sparsity result for moment constraint approximation of the Lieb functional. And here the sparsity reads as follows, in the sense that you can prove that for a number of moment constraints equal to big M, you can find some minimizers that are operators gamma, that are operators with rank at most equal to big M plus one, where big M is still the number of moment constraints in the problem. And so the fact that these guys are operators with rank, the dimensions of the range of which is quite small, will be amenable to some nice numerical scheme in the end. I just want to emphasize that still here, these operators still act over the set of wave function. So there is still some work to do in order to approximate these guys that are still quantities defined over the very high dimensional space. So here, there is a catch. But at least the range of these guys can be, the dimension of the range of this guy is not too large. Okay. So let me check the time. Okay. So that's for the sparsity results of that we get on some minimizers of this moment constraints approximations of the functional in the SC case and in the Lieb case. Okay. And so that's what I'm going to tell you about now is how we used these results in order to design some numerical schemes to compute approximations of either the SCE functional or the Lieb functional. So first, in the classical case, in the SCE case. So remember, as I told you, we know that we can get some minimizers of the moment constraint approximation under this sparse form that I just introduced to you. And for this, we need to identify the correct set of weights and the correct set of positions of the Dirac masses in the representation. Okay. So you want to say, okay, now what do I obtain if I restrict my minimization set to be the set of probability measures that can be written under this form, okay, with this sparse representation. And so what you obtain is then a minimization problem that reads under this form, where you look for a collection of k location of the Dirac masses and a collections of k weights, okay. And the moment constraints reads under this form here, and the cost reads under this form here, okay. So there is a catch in the sense that, okay, we've got a sparse representation, but the price to pay is that we end up with a non-convex minimization problem under non-convex constraints. Okay. So for this, to try to compute a solution to these minimization problems, we rely on some stochastic gradient algorithm of a constraint manifold, and the manifold is given by the moment constraints approximation here. Okay. For this scheme, we do not have convergence of the scheme towards a theoretical result guaranteeing that the scheme converges to a global minimizer of this problem here because of lack of convexity. We have some such partial convergence results, but on some particular assumptions on the moment functions and some particular assumptions on the cost, but which do not fit exactly in this density functional theory and for the Coulomb cost. We have it for attractive cost, and so this has some interest for other types of optimal transport problems, but we don't fit exactly in this framework. But we can still do some numerical tests and see what we obtain. Okay. So this is first some numerical tests in 1D with 5 electrons. Okay. So these are two choices of electronic density. So first, here we are in compact state space that is 1, 1, 1. Sorry, this should be Q. Oh, my apologies. And here we use Legendre polynomial test functions. Okay. So we consider first an electronic density that is uniform density, and a second electronic density that has this oscillative behavior. Okay. And so what do we obtain? So we first consider how the cost decays along the iteration of the stochastic gradient constrained algorithm, okay, for different values of the numbers of the moment constraints. So there is no surprise. So higher the number of moment constraints, the longer it takes for the algorithm to converge to some limit value. And here is what we obtain in the case of uniform density. Why do we do this numerical test? I should have mentioned it before. Is that in 1D, whatever the number of electrons, we know the analytical expression of the solution of the exact problem, classical optimal transport problem. And this is a probability measures defined over set R3n, which has a very sparse support. And you see here these red diagonal lines. So here, I'm plotting two particle marginals of this probability measures that is defined over R5 here. And in red here are the lines highlighting the support of the exact solution of the exact optimal transport problem. Okay. And so here what we are looking at, in these blue dots, these are the particles computed, the locations of the optimal particles computed out of the stochastic gradient algorithm I mentioned. And what you see is that these optimal points, they indeed concentrate around the support of the exact minimizer, okay, which is quite reassuring, at least numerically, because we don't have any theoretical guarantee of convergence of the algorithm. And this is what we obtain when we impose 10 moment constraints, 20 and 40. Okay. Again, here the constraints are the moment functions are Legendre polynomial, and this is a similar type of plots for the second electronic density with oscillations. Okay. And we see the same kind of behavior. Here again, we know the analytic form of the exact solution of the exact problems, and the support is materialized through these red lines again, and the blue dots are the location of the optimal particles computed from the stochastic gradient algorithm. Okay. And just to finish with the classical case, and then I'll turn to the quantum case. Actually, the stochastic gradient algorithm, because we use the sparse structure of minimizers, we could implement it on rather high-dimensional problems. Okay. For a number of electrons, so here are some results we obtained for a system of 100 electrons. with 52 polynomial test functions. And here the electronic density is a normalized sum of 6 quotient functions on R3. Okay? And so here what you see are various two-dimensional marginals of the minimizing measures that we compute out of the stochastic gradient algorithm. Okay? So we could identify such type of structures appearing. Okay, we don't have a real explanation of why this type of structures appear, but that's what we obtained with that. Okay. Let me now turn to the quantum case. So in the quantum case here, the numerical algorithms that we use to make the numerical tests that I'm going to show you actually rely on the generalization of the column generation algorithms that was considered by Guéraud-Frieseke in the classical case. Okay. Here, this algorithm will rely on the sparsity results that I've introduced, that I presented to you before, and it will read like an iterative algorithm, which will read as follows. Okay. How does it work? First, here, for the sake of simplicity, I'm going to assume that all the integrals are taken over the compact domain Q to the n instead of R3n. Then, if you make this assumption, okay, you can prove that the moment-constrained approximation of the Lieb functional is equal to the solution of a dual problem, okay, that reads under this form. So here, I've just rewritten the moment-constrained approximation of the Lieb functional here. And here, this is the associated dual problem, okay, which is under the following form. The dual problem for given electronic density rho. You look for an external potential V that belongs to the span of the first big M moment constraint, phi m, which maximizes the integral of V times rho under the constraint that the Hamiltonian related to minus V is still a non-negative operator, okay. So this is a dual problem associated to the primary problem, and thanks to this compact domain assumptions, you've got this, and the fact that you've got a finite number of moment constraints, actually you've got this equality. Okay. Okay. And the iterative algorithm actually solves alternatively some reduced primal problems and some reduced dual problems. So what do I mean by reduced? By reduced, I mean the following thing. These reduced problems will always use some finite dimensional subspace W, okay, of H0n, which will be rather low dimensional at each iteration. And it corresponds to solving approximate primal and dual problems, where in the primal problem case, you only look for operators gamma that act, that are operators acting on W, okay. And here on the dual problem, this reduced finite dimensional subspace comes into play into the constraint here. And you only impose that the projection of the Hamiltonian associated to the potential minus V onto the subspace W is non-negative. Okay? So these guys are what I mean by reduced primal and dual problems, and they depend on the choice of some finite dimensional subspace W. Okay? Actually, in practice, when you implement these primal and dual, reduced primal and dual problems, they both amount to solving some semi-definite programming problems. And there are lots of libraries in order to do that in practice. And so the iterative algorithms, its aim is to update these finite dimensional subspaces that plays the role of a support actually for this for the operators gamma in the primal problem alternatively. Okay. And again, at each iteration of the algorithms, these subspaces W, which will come, I'm going to tell you more precisely how they work, they will be low dimensional. Okay, so, and low dimensional, they will be of range roughly of the order of big M, the number of moment constraints. Okay, so more precisely, how does it work? So you start from some initial reduced space W0, which has to satisfy some assumption for the sake of time. I'm not giving more details about that. Then what you do first, you first compute an external potential for given, so sorry, at iteration n, so assume that you've got a reduced space Wn. You compute an external potential Vn plus 1 that is a solution of the reduced dual problem associated to the subspace Wn. Okay? More precisely, there may be several maximizers. You choose the one that belongs to the kernel of the linear functional defined by means of the electronic density rho. Okay? So this gives you Vn plus 1. So here, in the reduced dual problem, you only impose that the projection of the Hamiltonian on the subspace Wn is non-negative. So the full Hamiltonian could still have negative eigenvalues, okay? And that's the criterion to determine whether we have reached an optimal solution or not. Okay. So if the full Hamiltonian does not have any negative eigenvalues to stop the algorithm, we've reached an optimal solution. Otherwise, you compute the lowest eigenvalues of this operator and associated eigenvectors. And here, that's where we still have to solve high-dimensional eigenvalue problems so far. Okay, but well, we can't tackle all difficulties at the same time. This will be for future work. Okay, so you compute, let's say, QVec. QVec is a parameter that has to be defined by the users. Yeah? The QVec lowest eigenvalues of the full Hamiltonian and corresponding eigenvectors. So QVec in practice, we choose it to be 2, 3, 4. Okay, and then you define another reduced space. So it will be an intermediate reduced space, which I will denote by W tilde n plus 1. That is just the direct sum of the previous one, Wn, plus the span of the eigenvalues that you've computed. Okay. Then you've got W tilde n plus 1, and you can compute the solution of the associated reduced primal problem. Okay? So here, the dimension of W tilde n plus 1 is roughly big M plus QVec. Okay. So it's still much lower than what would be a full state space. Huh? Okay. This gives you a minimizer, which I denote by gamma n plus 1. And then, in order to go on with the iterative algorithm, you define the new reduced space Wn plus 1 to be the range of this gamma n plus 1. And this guy, also using the Chakalov theorem, you can prove that its range is, sorry, this should be an m, the dimension of its range is lower than m plus 1. Sorry, this should be an m. And you go on like this. Okay, you iterate, And what's nice with this algorithm is that you only compute reduced primal and dual problems of very moderate dimension. Okay. You can prove, out of this, the structure of the problem and so on, that this gives you a sequence of approximation for the level functional that is decreasing along the iteration. And then you compute, you converge it then, well, we don't have full convergence of the algorithm. We only know that we have a monotone sequence of approximation of the values at this point. So together with Rodrigue Lelot, I think under some assumption we've almost a convergence result, but we need to check the details. We're not completely there yet. Okay, so just some toy numerical test. We cannot do the full algorithm in high dimension because of these eigenvalue problems that I've told you. And we still have, at this point, to solve eigenvalues in the full state space. Okay. So here, we only have results on some moderate dimension problems. So here I'm going to show you some results for 2 electrons in dimension 1. And the state space will be the interval minus 10, 10. Okay. Here, the set of wave functions is discretized with Slater determinants. The molecular orbitals of which are discretized using P1, piecewise affine elements associated to a uniform mesh with 100 degrees of freedom. Okay. So that the eigenvalue problems are still computable. Okay, here. And the n moment functions will be piecewise affine functions. So just to make the link with your question, here these guys are piecewise affine functions. Sorry, associated to uniform mesh, and the number of degrees of freedom of the mesh will depend on the discretization parameter big M chosen. So first of all, in this algorithm, we wanted to study the influence of the parameter QVec, that is the number of eigenvalues and eigenvectors that we select at each iteration. Okay. So here what we plot is the value of the approximate value of the Lieb functional, okay, that we compute at each iteration of the algorithm. So this is for 20 moment constraints and for different values of this QVec parameter. So what we see is that the higher this parameter QVec, the roughly the fastest the convergence of the algorithm, but there is no tremendous difference, however. Okay, we see an effect, an improvement, but not there is no big significant effects. Okay, so that's the reason why in practice we choose QVec to be 4 or 2. Well, it depends. So here we took it to be equal to 4. So now we wanted to consider the influence of M, the number of moment functions. So as you see, so here you still see that the approximation is indeed decreasing along the iteration of the algorithm. And what you see is that indeed as M increases, the limit value decreases and becomes closer and closer to the exact value of the Lieb functional. So this is quite expected. One last thing that I want to show you, which I think quite interested, is how the potentials V, the optimal potential V, look at the end of the convergence of the algorithm. So this is our optimal potentials V solution of the dual problem look like for different values of the moment constraint. So this is for 10 moment constraints, 20, 30, 40. And you see that this potential V, it slowly converges to something, but you see some very high oscillations there. So just to have a look at what they look like. Okay, so I've finished, so thank you for your attention. So just to conclude, here we are considering some ways to compute approximations of the Lieb functionals and the strongly correlated electron functional by considering them as particular instance of quantum or classical optimal transport problems by means of these moment constraint approximations. Okay. So in the classical case, we consider some stochastic numerical particle scheme. Okay. And in the quantum case, so far we have designed some quantum column algorithms that is an extension of an algorithm that was previously considered by Guéraud-Frieseke. Why were we interested in trying to compute approximation of the Lieb functional? The hope, which is a long-term goal, okay, is the following. There is a there are some tremendous efforts in the computational chemistry community in order to compute some machine learning approximations of the Lieb functional. Okay. Here, what we would like in our most crazy dreams, we would like to try to go rather in the direction of constructing approximation of the Lieb functional by means of machine learning, rather than the level Lieb. Because the Lieb functional is convex, we hope that this would lead to better scheme and better approximate models for electronic structure calculation in the end. And so let's say it's a modest step towards this direction. Okay, we don't know how far we will get with that. And with this, I thank you for your attention, and I'm over. Thank you.
So are there questions or comments?
There is this recent paper by forgot the name, Cavallo. They proved that in 1D the dual V exists.
Yeah.
And in H-1, so you can have some delta. So
yeah.
I'm wondering whether you see some delta.
Almost. You see these big peaks, I think they are approximation of the deltas. I'm not sure because you see.
What's the size of your mesh, and is it of this?
So here the mesh is 40. Okay. What makes things a bit difficult is that here there are two grids. There is one for the approximation of the eigenvalue problems. Okay. And this we take it as large as we can, but we can't go too far so far. Okay. and there is a 1 for the V. And what we see is that we need the grid for the V to be coarser than the grid for the wave functions. Otherwise, we've got strange results.
Do you
And so
believe that you have 3 deltas or even negative deltas? Or what
I don't know, because here you see it's not completely clear, because here the amplitude remains quite small, but the discretization is too coarse to really give a full answer to your question. At least what it shows that there are higher oscillations and.
it seems to be growing with M.
Yeah, a little bit, but not too quick. It's not exploding, but that M is not very large. So I don't know. I don't know.
So I have a rather naive question. But, so if I understand correctly, so you have an algorithm basically to compute the dual potential, so to say. But if I understood correctly, the algorithm involves basically checking that the ground state energy be positive, meaning you have to compute the ground state energy of the many-body problem.
Yeah.
Now, I thought that's the thing that's numerically very hard and that density functional theory is solved. So if I have to solve it, to compute dual potential, what have I gained numerically?
So here my hope is the following, is to use there some approximate ways to compute these guys here. Okay.
But isn't that the original problem, approximate ways to compute the ground state energy of the many-body Hamiltonian?
Yeah, but here my hope is the following, is that you can do that in an offline way for some electronic density rows, for some of them, okay. Then learn the Lieb functional out of it for some particular electronic density rows, and construct an approximation of the Lieb functional that will be used for other type of electronic densities. In the same way that the people I mentioned, they are doing that for the Lieb functional. Okay. So whether it gives reliable approximation or not, it's still under debate. Okay. But that would be the hope, in the sense that you do very expensive calculations for some particular rows, and then in an online, in the online phase, you use this approximation in order to solve, to compute optimal electronic densities for a large number of systems. Because here, what is nice is that you've taken away somehow the influence of the external potential. But well, you're very, very, very far from that. I'm not claiming anything.
Thank you.
And nevertheless, just having just from a theoretical point of view, having some illustration of how approximation of this potential look like. Well.
Other questions or comments? So if there are none, I suggest that we thank Virginie again.
Thank you.